As we have seen, taking a derivative by simply using the definition of derivative can be a very time-consuming matter. So what we need is a few shortcuts, a few formulas to make the derivative go just a little bit faster. Now, these all can be proven. A lot of the proofs are in your textbook, but proving them is very time-consuming. So for the sake of just saving some time, I'm just going to just put them out there, show you the formula, and put it to use. All right, so in no particular order, first off, the derivative with respect to x of a constant is always 0. Now that one, if none of the others, that one should be pretty obvious as to why it works that way. Remember, derivative gives you instantaneous slope. And if you were to graph f of x equal to a constant, or y equal to a constant as it's sometimes expressed, if this is your x-axis, this is your y-axis, what you always get is a horizontal line striking the y-axis at that value. All right, now whether that line is on the positive side of the y-axis or the negative side of the y-axis won't make any difference. The slope of a horizontal line is always 0. So that sort of reinforces what this is saying as far as this derivative is concerned. All right. There are, as a matter of fact, there are other functions whose derivatives should be obvious. If you look at f of x equals x, which is your identity function, that's a straight line passing through the origin with a slope of 1. So therefore, the derivative with respect to x of x, logic would dictate that ought to be a 1. So again, there's a couple of them that's pretty obvious. The next rule might be a little bit more subtle. Again, not really bad to prove, but that's not going to be our focus right now. The derivative with respect to x of x to the nth power is going to be n times x to the n minus 1 power. So basically, when you take the derivative of a variable base to a constant power, you really have to emphasize that. Variable base, constant power doesn't work if it's the other way around. Variable base, constant power. The power comes out front, and then the power decreases by 1. All right, so, for example, the derivative with respect to x of an x to the 4th would be a 4x cubed. This actually would work. This rule can be used in a lot of places, a lot more than what the book would often indicate. It can be used for our derivative with respect to x of x. If you remember that x is to the first power, this would simply say, bring the 1 out front, take the x down to the next lower power, which would be 0 power. X to the 0 is 1, and 1 times 1 is 1. So that kind of reinforces the last one that I mentioned. Power rule sort of validates what we said the last time around. So that is your power rule. Again, not always big myself on remembering the name of everything, but that one gets used a lot. Therefore, it doesn't hurt to know that name. Now, I demonstrated it here with an integer power, and a lot of books will state this rule 2 or 3 times, and they'll say, here's how it works with an integer, here's how it works with a decimal, here's how it works with a fraction. That's all completely unnecessary. Power rule works the same way every single time. If I had an f of x equaling 1 over x to the 5th, you would simply rewrite that as an x to the negative 5th. And f prime of x in that case would be a negative 5, x to the negative 6. Now, if you felt inclined, move that x back down to the bottom and make that a positive power, knock yourself out. But you don't have to. If you had a g of x equaling the 5th root of x cubed, you would simply rewrite it as x to the 3/5 power. And g prime of x would be 3/5 times x to the negative 2/5 power. I just took 3/5 and dropped it by 1. And again, if you felt inclined, put it back in radical form and positive power form, feel free to do so, but it's not really mandatory. All right, so you can now take the derivative of a variable, any constant power that you want. We can expand that. If you want to take the derivative with respect to x of a constant times f of x, in other words, if you have a constant set in front of a function, and you want to take a derivative, what can happen, and you're going to find this to happen with derivatives, you're going to find this to happen with integrals as well, is the constant can basically be bumped out front, and it just gets multiplied by the derivative of f. So if I had a h of x equaling an 8x to the 5th, and I want to take h prime, and again, notice I'm switching back and forth from one notation to the next because you need to get comfortable with all of them. That'd be 8 times, now I'm just going to take the derivative of x to the 5th, to 5x to the 4th. 8 times 5 is 40, 40x to the 4th. On the other one, I said if you want to move the negative powers around, do it. If you don't want to, not really the end of the world. But if you leave it this written as an 8 times 5 and don't call it a 40, then there's something wrong. All right, you just need to go ahead and do that multiplication. We also have a sum rule, as it can be called. The derivative with respect to x of f of x plus g of x is the derivative with respect to x of f of x plus derivative with respect to x of g of x. So if I had an f of x equaling a 5x to the 3rd plus a 2x squared minus a 3x plus 8, what this sum rule will allow us to do, let me put a plus in there so I'm technically not breaking the rules. I can find f prime of x by taking the derivative of these one at a time. The 3 would come down, and you should be very quickly getting to where you can do this in your head. 3 comes down, 5 times 3 is 15, power drops. 2 comes down, 2 times 2 is 4, power drops. Derivative of the constant sitting in front of the function would be a 3 times derivative of x, which is 1, which is a 3. And derivative of 8, since 8 is a constant, would just be 0. All right, you should be able to get to the point where you can do these very rapidly. We have a sum rule, by the way, and we have a difference rule. It basically says the derivative of a difference is the difference of derivatives. All right. So therefore, derivative with respect to x of x to the 8th plus 12x to the 5th minus 4x to the 4th plus a 10x cubed minus a 6x plus 5. And let me point out that is something that would be particularly unpleasant to try to do by the definition. But again, for this one, remember that was an 8. It wasn't clearly written. 8 comes down, power drops. 5 comes down, you multiply, power drops. 4 comes down, you multiply, power drops. 3 comes down, you multiply, power drops. And then a 6. And that is it. The derivative of 5 would be 0. These rules, these tricks, these shortcuts, these formulas, whatever name you feel like calling them by, will save you a phenomenal amount of work. Everybody, of course, chooses to use them. You'd have to be self-destructive going to do the derivatives by the definition time and time again when you don't have to. All right? So there's a few of the rules down, and at this time it's pretty common to discuss how the base of the natural logarithm, a number that's commonly symbolized using the letter E, came into existence. All right. There was a mathematician named Euler, pronounced like oil, like motor oil, but spelled E-U-L-E-R. And Leonhard Euler wanted a number such that when it was used as the base of an exponential, it would be its own slope. Here's what I'm talking about. All right. If you graph y equals e to the x, again, that being an exponential with a base larger than 1, you will get exponential growth. All right. If you look at this function at any location, and let's say you look at it at an x value of 1, the y value will just be e to the first power. If you look at it at an x value of 2, the y value would just be e squared. If you were to come in and measure the slope of the tangent line at any of those locations, you'll find that the slope of the tangent line is equal to the y value. All right, so basically it is its own slope. All right. So therefore, to make that happen, the number had to be defined in a particular way. All right. Again, we approximated, I guess I should say approximated, it's about 2.71, 828, et cetera, et cetera, et cetera. But the number e is the number such that if you take the limit, as h approaches 0, of e to the h minus 1 over h, you get 1. And this is just sort of a fancy way of saying its slope at 1 is e to the first. All right. So regardless, that will come up later. It's a very important function. It is therefore a function that is, what this all boils down to, is a function that is its own derivative. It was created specifically for that purpose. In other words, the derivative with respect to x of e to the x is e to the x. That is not something you will find every day, and that's putting it lightly, but the derivative of e to the x is e to the x. It is a function that is its own derivative, and it is pretty much the only function that is its own derivative. Any trivial function, non-trivial function that is its own derivative is e to the x. All right. So moving on, we have a couple other rules we need to establish. These first rules are quick and easy to use. The ones that come after get a little bit more complicated. Again, they can be proven, but that's not going to be my main goal. All right. So next rule is called the product rule, derivative with respect to x of f of x times g of x. With your addition and with your subtraction, you're able to just basically distribute. With this one, not going to work like that. Straight up, just distributing will not work. This one is usually, in most textbooks, written as f of x times derivative with respect to x of g of x. And I think they will, they'll use brackets or braces or something usually. Plus g of x times the derivative with respect to x of f of x. And that is honestly a very confusing way to write it. A better way to write it, I believe, is f times g prime plus g times f prime. I think that just is faster. Most people memorize it by saying first derivative of second plus second derivative of first. That's the way it's most often done. So, as an example, if your f of x was equal to x times e to the x. And you want to take the derivative, you would go first, here's your first, here's your second. First derivative of second plus second derivative of first. Again, this will clean up just a little bit, not much. Just by not having to write down the one, that cleans it up a tiny little bit. All right. So that's your basic product rule. If you had, for example, something like y equal to, let's use the y equal to notation a little bit, not always use f of x, and e to the x over an x squared, and you really, really wanted to use the product rule, you could rewrite this as e to the x times an x to the negative 2 power. And therefore your y prime would be first, which is e to the x, derivative of second, which is bring down the power, drop the power by 1, plus second, derivative of first. Again, a little bit of cleaning up that could be done. You could put the negative 2 next to e to the x. You could put the x to the bottom with a positive 3 power. And put the 2 to the bottom with a positive 2, the x to the bottom with a positive 2 power. All right? That is your product rule. It gets used a lot. You will have to memorize it thoroughly. Now, of course, this problem was originally written in the form of a quotient. So therefore, it could have also been done with what's known as the quotient rule. Derivative with respect to x of f of x over g of x would be equal to, now again, this one can be written in a long notation, but it's really not necessary. Let's just cut to the shortcut like this one up here. Here's the way I have it memorized. Bottom, derivative top, minus top, derivative bottom, or bottom, squared. Right, that is your basic quotient rule. So if we again had an e to the x over an x squared, would we get the same answer if we used the quotient rule instead of rewriting it and forcing it to work with the product rule? Of course we would. Y prime bottom is x squared. Derivative top is e to the x. Minus top, which is e to the x. Derivative bottom is a 2x. The bottom squared is an x to the fourth, because a squared is a fourth power. And you're like, well, that doesn't quite look like what we had. Yeah, it does. Split it up. X squared e to the x over x to the fourth minus 2x e to the x over x to the fourth. Reduce the fractions. And I think you'll see it's the same thing. I believe you'll find that that is the same thing. All right, so what do we have going for us now? Well, shortcuts that make these derivatives go a whole lot faster. Derivative of a constant, we now know how to do. Power rule, we now know how to do. Again, when the power is a constant, the base is the variable. Derivatives of sums, derivatives of differences, derivative of e to the x, product rule, and quotient rule. Practice them because you will have to use them extensively. So make sure you practice them.